Okay, so in this lesson, we're going to look at the fundamental counting principle, and this is in section 11.1. 11.1. All right, so the the so let's begin by just looking at this example here, and this is in your uh, Canvas section. So just go and make sure if you need to that you download this. I'm going to go ahead and enlarge this to make it look a little bit larger. All right, so let's look at what this says. So the fundamental counting principle, and we're going to see what that really looks like in words in a little while, but the fundamental counting principle is a way of determining the number of possible ways that we can perform two or more operations together. And you can see what that means when we look at this example and the other one. If the operations were performed independent of each other instead of together, then we would not use the fundamental counting principle. All right. Now, in this first example, we're going to do this instead of using the fundamental counting principle. We're just going to use an idea that you learned probably in middle school, and that's the idea of the tree diagram. Okay. All right. So let's look at the first example. All right, a school cafeteria restaurant offers a lunch combo for $6 when a person can order one sandwich. So you must order, in this example, you must order a sandwich, you must order a side, and you must order a drink. Okay? And so that's the idea of uh, the operations or the events being done together. Okay, so these operations are being done together. Okay, they're not independent. Independent would mean I can order a sandwich if I want to. It doesn't matter. I don't have to order a side. I don't have to order a drink. I can order a side. I don't have to order a sandwich. I don't have to order a drink, and so on. Okay, so that would be independent. In that case, you would not use the fundamental counting principle. But in our example, in examples here, these operations are going to be done together. So every event will be done together. So you must order a sandwich, you must order a side, you must order a drink. Okay? That's assuming you do all three. All right, if you don't do all three, then we cannot use the fundamental counting principle. All right, so let's look at this example again. So example one, a school cafeteria restaurant offers a lunch combo for $6 when a person can order one sandwich, and the sandwich consists of either a chicken, turkey, or grilled cheese. Okay? One side, so your side can be a fruit, yogurt, or soup. And then one drink, and the drink is either juice or milk. Okay? Now draw a tree diagram or create a table to determine the possible lunch combos. So we're going to do a tree diagram. All right, now the way I would do this is see how you have a sandwich, and then you have a side, and then you have a drink. Okay, so that's the way that I would do this. And so in terms of the sandwich, your choices are chicken, turkey, grilled cheese, right? So I can choose a chicken. I'm going to go ahead and abbreviate. I can choose a chicken. I'm going to leave some space here. I can choose turkey, and I can choose a grilled cheese. Y'all agree? All right. Now, so let's say I picked a cheese sandwich. Then I got to pick one side, right? And so my side is either a fruit, yogurt, or soup. So if I pick a chicken, then I can choose my side being a fruit, or I could choose yogurt, or I can choose soup, right? Okay. If I choose if I choose a turkey, then I can, again, my side could be a fruit, yogurt, soup. If I choose grilled cheese, if I choose grilled cheese, my side can be fruit, yogurt, soup. Y'all agree with that? Okay. So that takes care of the side. So my order, I want you to look at what's happening. My order can be chicken, fruit, chicken, yogurt, chicken, soup, turkey, fruit, turkey, yogurt, turkey, soup. Grilled cheese, fruit. Grilled cheese, yogurt. Grilled cheese, soup. Okay? But then I have a drink to go by. So my drink can be either juice or milk. So you're going to say juice, milk. Juice, milk. So what's happening is this. If I choose chicken and my side is fruit, then I could either choose my drink to be either juice or milk. Same thing here. Chicken, yogurt, juice or milk. Chicken, soup, juice, or milk. Okay? And then turkey, fruit, same thing. Juice, milk. Juice, milk. Juice, milk. Juice, milk. Juice, milk. Juice, milk. You see that? Okay? All right. Now what's happening is this. Let me just show you. So here I'm going to go ahead and just go ahead and list the possibilities. So these are my possibilities, and I'm not gonna list all of them because I may not have enough room, but we'll see. So these are all my possibilities. So I can have one possibility being this. The first one is chicken, fruit, juice. Y'all agree? One of my other friends can get chicken, fruit, and what else? Milk. Chicken, fruit, milk. The third one can be chicken, yogurt, juice. Y'all agree? Chicken, yogurt, juice. A fourth friend can have chicken, yogurt, milk. Chicken, yogurt, milk, and so on. Y'all agree? Okay, and so on, and so on, and so on. And then finally, I can have another friend can have, I'm going to go put a number right here. Another friend can have grilled cheese, all these combinations, grilled cheese, soup, and what else? Juice. Grilled cheese, soup, and what else? Milk. So grilled cheese, soup, juice, and then grilled cheese, soup, milk. Okay? So if I count all these possibilities right here, how many do you think there are? Now I know I have a lot of them left off, but can you kind of determine how you could figure this out? All right, so yeah, one way would be to count these little ends right here, right? Those little endings. So this is your begin, and then you end here. So those little ending arrows, I guess you can say. So you have 1, 2. See, this one pertains to this one. Y'all agree? That pertains to this one. That pertains to this one. That pertains to this one, and so on. Y'all agree? That pertains to this one, and that pertains to this one. So if I count these, that's number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is number 17, and this is number 18. So how many possibilities are there for a lunch combo? So there are 18. There are 18 possibilities for a lunch combo. Okay, 18 possibilities. All right. Okay, so we did this using a tree diagram. All right, so that's the way I would do a tree diagram. So basically, in these examples, you'll be given situations like this, and so you just list them, just like that. All right, and then you have your possibilities. Now, this part was not necessary. This is your tree diagram. I was just explaining what your possibilities would be if you listed them like this. All right, and so notice there are 24 of them. So we just counted. Okay. All right, let's look at the next example. Example 2. Okay, so example 2, let me find it. Okay, example 2. Actually, this is still, I guess, the first example. All right, so look at what it says. It says, oops. All right, so let me go ahead and enlarge it to make it a little bit better for you to see. So basically it says, suppose we add an extra type of sandwich, an extra type of side dish, and an extra type of drink. What impact would this have on our tree diagram? And then would it still be feasible to use a tree diagram? Okay, so basically what that's saying is this. Let me go ahead and get another sheet of paper out. So what that's saying is if you were, okay, if you were to kind of do this right here, the tree diagram again. So you see right now you have, it says you have an extra type of sandwich, right? So that means instead of 3 sandwiches, you have how many? You have 4. You would have 4 sandwiches. Instead of 3 side dishes, how many would you have? You would have 4 because you're adding an extra type of side dish and then an extra type of drink. Instead of having 2 drinks, you would have 3. So let's think about in our mind, if I were to draw a tree diagram, what that would look like. All right, so I would have my let's say, how do we call this? We used okay, so this would be the sandwich, and so I'd have a sandwich 1, sandwich 2, sandwich 3, sandwich 4. Y'all agree? All right, and so let me go ahead and do this, and so then you would take care of, what was the other one? The side dish. But look what's going to happen. So now you have 4 as well. 1, 2, 3, 4. 1, 2, 3, 4, and so on. Y'all agree? But then notice what happens. You then have an extra drink. So then your drink, remember there are now 3 of them, you'd have to do this. 1, 2, 3. 1, 2, 3. 1, 2, 3. You see what's happening? It's becoming so cluttered, that using a tree diagram with that many possibilities is just not feasible. Okay, so what I would say here, suppose we add an extra type of sandwich, an extra type of side dish, an extra type of drink. What impact would this have in our tree diagram? I would say it would become too messy. All right, too messy. You can see that right now, right? That's just too messy. Too cluttered. Okay, and then is it feasible? No, it's not feasible. No, it's not feasible. Okay. So that brings us to this. Then what are the limit of the tree diagrams? I know that in the problem we just did, it was feasible. It wasn't that bad. I could have easily done this on paper, the one we just did. All right, so that's the one that we had 18 possibilities. So what are the limitations of doing this? Well, the limitations of doing this, if I would use a tree diagram when you have a small number of events. Okay, small number of events. Just like this. I mean, it's just like I have 3. I have 3. My first event, there were 3 choices. My second event, they're calling these events. My second event, which was a side, had 3 choices, and my third event was choosing a drink, had 2 choices. But when you start increasing any of those, it does become a little bit messy. All right? Okay. So, in cases, now this is important, in cases where there are a large number of operations being performed together, like the one we just did, you now have 4 sandwiches, 4 sides, 3 drinks. In cases where there are a large number of operations being performed together, it is not feasible to construct a tree diagram. It is more reasonable to use a fundamental counting principle. And that's what this section is about, the fundamental counting principle, to determine the number of ways of performing all tasks together. All right. So here's the idea. I want you to notice something, and then we're going to talk about the fundamental counting principle. Let's go back right here. So remember how we got 18 possibilities using the tree diagram, right? Okay, there are 18 possibilities. I want you to notice, I'm going to go ahead and just do this right here. So looking at example 1, I want you to notice something. So when I looked at the sandwich part, when I look at the sandwich, how many possibilities were there? How many possibilities were there? That was a chicken, that was a turkey, there was a grilled cheese. So I'm at the counter and I can choose how many possibilities. I can choose how many possibilities for those. I have a choice of how many? 3, right? So I'm going to put a 3 here for the moment. Then I had a side drink. A side. Excuse me. And so when I look at the side, remember how many sides were there? There was like fruit, yogurt, soup. So how many choices did I have? I had 3. Y'all agree? And then finally, let's look at the drink. The drink. And so when I look at the drink, I can choose from how many of those? 2. I could have chosen either juice or milk. Now, I want you to notice something. What happens when I multiply 3 times 3 times 2? What number do I get? 3 times 3 is 9. 9 times 2 is 18. I get 18, right? So that is what we're using here is the fundamental counting principle. That is a fundamental counting principle. So rather than using a tree diagram, and notice it took us a little bit longer to do, rather than using a tree diagram and counting how many branches I have, counting all those branches, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Rather than counting all those branches, I could have just said, all right, since all of these, since those are not independent of each other, because I must choose this, I must choose this, I must choose this, then I can use a fundamental counting principle. I have 3 choices to choose from for the first one. For the sides, I have 3 choices. And for the drink, I have 2 choices. So I can just multiply those numbers together. And that's going to give me the number of possibilities, number of possible combos in this case. Okay? All right, so that's called the fundamental counting principle. And basically, the fundamental counting principle says this. Okay, look at this. So it says, go ahead and enlarge this. So it says, and look at what we have here. So if we want to perform a series of tasks, and the first task can be done in A ways, so in this case it was 3, and the second can be done in B ways, in this case it was 3, and the third can be done in C ways, in this case it was 2, and so on, then all the tasks can be done in A times B times C times however many tasks you have ways. So 3 times 3 times 2. So that's 18 ways. Okay? Isn't that an amazing principle? That's pretty cool, isn't it? All right? So we don't have to do all this work. We can just use the fundamental counting principle. All right, so let's look at some more examples. All right, so just kind of reviewing what we did. All right, so we talked about the fundamental counting principle, which basically says the number of ways of performing tasks together would be the number of ways for the first task times the number of ways for the second task times the number of ways for the third task, and so on. Okay, so if we look at that lunch combo, which we did, that's this example right here. So that's the one we just talked about. Okay. Let me quickly find it. That's this. All right. So that would go here. All right. So note, I just want you to remember something. Note that the fundamental counting principle can only be used when each of the given tasks are being performed together. So remember, we chose a sandwich, we chose a side dish, and then we chose a drink. So they're being done together. From our example, there are three tasks: sandwich, side dish, and drink. A lunch combination consists of all those three tasks. Okay? That is, it could not include just a sandwich or just a side or just a drink. If I could just go and order a side dish or a drink, then I could not use the fundamental accounting principle. Okay? All right. Now, let's look at this example. So this will be example 2. Example 2. In how many variations of ice cream sundaes can be made if the ice cream choices are vanilla and chocolate, the toppings are nuts or candy pieces, and the sauces are chocolate, fudge, or strawberry? Each sundae must contain one type of ice cream, one topping, and one sauce. Draw a tree diagram to show how many different sundaes can be made, and then verify the solution using a fundamental counting principle. All right, so basically, let's see, there's not that many, so we should have enough space here. So it says you must choose one type of ice cream, so ice cream. Okay, ice cream, and then I could choose from, what was it, vanilla and chocolate, so VC, vanilla and chocolate. Then I could choose a topping, all right, my topping, and I had either nuts or candy pieces, so nuts, candy pieces, let's call it CP since I already have a C here, and then nuts, candy pieces, right? And then the next one was one sauce, and my sauce could be either chocolate, fudge, or strawberry. So sauce. Now I guess I should have. I'm not gonna have enough room, but chocolate. What was it? Chocolate, fudge, or strawberry? So C, F, S. C, F, S. C. I don't have enough room. F, S. I don't want to just dismiss this problem. Let's just actually do it since I'm going to go ahead and use a better sheet of paper. So ice cream. So vanilla, chocolate. Topping. What was it? Nut or candy pieces? I'll just go do P for candy pieces. And then chocolate was nut or candy pieces. Okay. Then my sauce could either be chocolate, fudge, or strawberry. Chocolate, fudge, strawberry. Chocolate, fudge, strawberry. Chocolate, fudge, strawberry. Chocolate, fudge, strawberry. Okay? All right. So how many branches do I have? I have 1, 2, 3, 4, 5, 6. See what's happening? I could choose vanilla, nuts, chocolate. Vanilla, nuts, fudge. Vanilla, nuts, strawberry, right? Okay, so just count how many of these branches you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I get 12 possibilities. Y'all agree? All right, now let's verify that. Using the fundamental counting principle. So the fundamental counting principle would be the number of choices for ice cream, which is 2, times the number of choices for topping, which is 2, times the number of choices for sauce, which is 3. So 2 times 2 is 4. 4 times 3 is 12. Okay? All right. Example 3. So, and I'm going to go ahead and use this rather than using ours in the United States because it varies by state. And in Louisiana, I guess we could have used Louisiana's, but let's just go ahead and use this one. Newfoundland and Labrador license plate consists of a letter, 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 digit, digit, digit arrangement such as this, right? Kind of the same thing in Louisiana, I guess. You have the 3 letters and then you have the 3 digits. How many, so here's the question, how many license plate arrangements are possible if both letters and digits can be repeated. All right. So notice that in Louisiana, and this could have been Louisiana, you can have AAA, BBB, and so on, right? Okay. You can have 111, 222, 333, and so on. You can have 334, A, B, B, things like that. All right, so that's what we mean by repeated. All right, so I'm going to use the fundamental counting principle. So the number of possibilities. All right, now listen to the words. Number of possibilities will equal. All right, so let's talk about the first letter, our first letter. So how many letters are there in the alphabet? Well, there are 26, right? So I'm going to put a 26 here. Times. The second letter, I can still use, if I chose a B here, I can still use a B, right? So how many letters are there? 26. Times. Third letter, how many choices? I can repeat. 26. All right, let's talk about the number. All right, now remember, this is one digit. Let's talk about the first one. So that could be a 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So notice 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many choices are there? That's 10. So for each digit, there are 10 choices because I can repeat. Now using your calculator, how many possibilities are there? So 26 times 26 times 26 times 10 times 10 times 10. Notice, would you want to do a tree diagram for this? Look at this. So it's like 76,576,000 possibilities, right? Okay, let's get the next one. How many license plate arrangements are possible if no letter or digit can be repeated? Okay, no letter or digit can be repeated. So number of possibilities. Number of possibilities, okay, will equal. All right, so let's talk about that first letter. So how many choices do I have for that first one? 26, right? Okay, now let's talk about the second one. So I can't repeat. So I have all my alphabets. Let's say I chose A. How many letters are left? 25, right? Okay, 25, because I can't repeat it. If I choose B here, I can't use it here. Cannot. So I have 25 left. All right, now let's go about the third letter. So let's say I chose an A and this was a B. How many letters are left? 24. All right, so not repeated. No letter can be repeated. And then, or digit. So let's talk about the digits now. So remember there were 10 digits to choose from. I've already chose a digit, so how many are left? 9. I've already chose another digit, so how many are left? 8. Okay, so that's how you do that one. So that limits the number of possibilities. But our state does this one. So this is our states. All right, so you have 26 times 25 times 24 times 10 times 9 times 8. And so that gives you, see, it's less, right? So 11,232,000 possibilities. All right, so let's look at this one. Letter C. How many license plates are available if vowels are not allowed but repetitions are permitted? Okay, so let's talk about our vowels. So here are our vowels. A, E, I, O, U. Okay, A, E, I, O, U. So these are not allowed. So that means that from our alphabet, I've got to take these away. All right, so if I take these away, I have how many letters of the alphabet left? Left are how many? So 1, 2, 3, 4, 5. So there are 26 altogether, right? So if I take these 5 away, I'm left with 21. Y'all agree? All right, so let's do the number of possibilities. All right, number of possibilities. All right, so for the first letter, how many possibilities are there? And it says that it can be, repetitions are permitted. So 21. Second letter, 21. Third letter, 21. Now let's look at the numbers. The digit. All right, so now notice that it only had a restriction on the letters. So the digits, there are no restrictions. So there's 10, 10, 10. All right, so using the fundamental counting principle, I'm going to multiply those together. So I get 21 times 21 times 21 times 10 times 10 times 10, and it looks like you get this number. So 9,261,000 possibilities. Okay? All right, so that was example 3. So it's a pretty clean example, easy to understand in terms of the fundamental counting principle, right? Okay. So let's look at this next example. All right, next example. So, and it says example 3. I guess it should be example 4. So Canadian postal codes consist of letter, digit, letter, digit, letter, digit arrangement, right? Okay, you don't know that, but supposedly it does. All right, so let's look at how many codes are possible if repetitions are permitted. Okay, number of possibilities will equal. All right, so the first one's a letter, second one's a digit, third one's a letter, next one's a digit, next one's a letter, next one's a digit, right? Okay, so let's do the first one. It's a letter. Repetitions are permitted. How many are there? 26. Next one's a digit. How many repetitions? I'm sorry, how many possibilities? 10. Next one's a letter, 26. Next one's a digit, 10. Next one's a letter, 26. Next one's a digit, 10. And if you multiply that out, that's kind of the same number here, isn't it? So that's going to be this number. So it'll be 17,576. I'm sorry, 17,576,000. So using your calculator, you would get that. But that's this, because you see what it says. Remember, multiplication is commutative. The order in which you multiply does not matter. So do you see 26 times 26 times 26? 26 times 26 times 26? 10 times 10 times 10? 10 times 10 times 10. So you should get the same thing. Okay, so let's suppose that in Newfoundland and Labrador, all postal codes begin with the letter A. Okay? All postal codes begin with the letter A. How many postal codes are available? Again, repetitions are permitted. Now listen to this carefully. Okay. Number of possibilities. All right. So we have letter, digit, letter, digit, letter, digit. Okay? All right. So I'm going to go ahead and put those things here. So letter, digit, letter, digit, letter, digit. Y'all agree? Okay, now the ones that's going to cause you a little issue is this one. Let's look at this. So you're told that the first one must be A, right? So how many choices do you have for the first one? There's only one choice in it. It must be what? A. There's only one choice. It says it must begin with what? A. So you're told it must be A. You have no other choice. It didn't say it could be A or B. If it said A or B, then what would go here? 2. If it said A, B, or C, what would go here? 3. But it says it must be what? A. So what goes here? 1. There are no restrictions on the others. So how many digits are available here? Repetitions are permitted. 10. Letters, how many can you choose from here? 26. You can still use A. If A is here, A can be here as well. Then you have 10, 26, and possibility for digits, 10. Okay, use your calculator. Well, let's see what we get. All right, so that's going to be 10 times 26 times 10 times 26 times 10. So number of possibilities would be 676,000. Okay? All right, example 4. You go to order a meal. You have 2 choices for an appetizer, 3 choices for an entree, 4 choices for dessert. How many different meals can you have if you choose 1 appetizer, 1 entree, and 1 dessert? So that's a straightforward one. So number of possibilities will equal, Okay, so you have three things, right? Three events. First event, for the appetizer, how many choices are there? Two. Second event, which is the entree, you had three. Third event, which was the dessert, there are four. So 2 times 3 is 6, 6 times 4 is 24. All right, how many words containing three letters can you make out of the letters math? So that's kind of like that alphabet letter thing, the alphabet digit situations we had. So I want to make three letters, right? So number of possibilities. Okay, equal three letters. All right. So I want to find out how many words I can make containing three letters just using those right here. Now it says assume letters cannot be repeated this time. All right. So just think about it this way. So I'm going to just go ahead and kind of do like a little circle thing. I'll put math, the letters of math in here. Okay. So let's look at the first letter. So I'm about to take one of these letters out, right? So how many choices are there? There are four. Okay. Repetitions are not allowed. So I've already picked, let's say I picked M. So I've already taken M out. How many letters are left? Three. So let's say I chose M and T. So let's say this is M and this is T. So how many letters are left? Two. Y'all agree? All right. So repetitions, assume letters cannot be repeated. So to begin with, how many choices were there? Four. Let's say I picked M. How many choices are left? Three. Let's say I picked A. How many choices left for the last one? Two. Okay? All right. So altogether, there are how many possibilities? 4 times 3 times 2 is 24. All right. So I think that would be the end of this part. So that should help you with the My Math Lab and with the assignment that goes with this. So this, remember, this involved the fundamental counting principle. The fundamental counting principle. Okay.